So today we're going to talk about a new derivative rule. It is called the product rule. And so basically it says that the derivative of a product is equal to the derivative of f. So if we're doing the derivative of f times g, then this is equal to f prime times g plus f times g prime. Okay, I'm not going to prove this today because we can talk about this in class, and there's also an example in the book, so we're just going to use it today. So first of all, I just kind of want to show you, this isn't a proof, that it does in fact work. So we do know how to do the derivative of f of x. It's x cubed. So f prime of x, right, we can just use our power rule here, which is 3x squared. Okay, so this time what I'm going to do is instead I'm going to write f as, so this time I'm going to call it h, and I'm going to call it x squared times x. Okay, and so I want to first point out, right, we've already done this, and we know that this is true, that the derivative of products does not work. I can't just do the derivative of this times the derivative of this, because if I do the derivative of this, which is 2x, and then the derivative of this is 1, these two guys are not equal to each other, right? This is not the case. And so we have to use the product rule here. Right? So we're going to write h of x is equal to x times x squared, and we're going to call this one f and this one g. Now, when I'm doing this, so I have the derivative of one times the other plus then the plain other times the derivative of the other. So essentially, as I'm doing a derivative of each one separately and then the plain other in each case. Because of addition, it doesn't matter in what order. In multiplication, I could write g times f prime or g prime times f with this opposite. I could also have this one. There's like 4 different ways that I could write this, but as long as I have the derivative of one times the plain other and then I flip-flop, I do the derivative of the opposite times the plain other, then I'm good. All right, so my h of x, I recommend that when you get used to using the product rule that you write it out. I kind of write it like this. I write it twice, and then I use a little tick mark to say, okay, well I need to take the derivative. It doesn't matter which one. I'm going to do the derivative of this one in this piece, and then this one in this piece. Okay, so I've just written it out twice. So I'm doing the derivative of the x term in the first one, doing the derivative of x squared in the second one. All right, so the derivative of x is 1 times x squared, and then over here I have x times the derivative of x squared, which is 2x. All right, so I'm just doing each derivative and multiplying. So the derivative of x is 1 times x squared plus then x, then times the derivative of x squared, which is 2x. I'm just using the power rule on these. All right, so then what I have here is x squared plus x times 2x is 2x squared, and now this is actually 3x squared. And this in fact matches this up here. Okay. Now the thing is with the product rule at this time, there's not that many interesting examples in which I can force us to use the product rule. Like, I mean, a lot of the things that we can use the product rule on, we could actually just do the multiplication first and then use the power rule on. But it is important to get used to the product rule because we will be coming into different functions that'll be much harder to just multiply out in order to use it on. So here's a reasonable example. So I have f of x is equal to the square root of x times this x cubed plus 2x plus 4. So the first thing I'm going to do is rewrite f, because whenever I see the square root, I should immediately think, oh wait, I have to write that as a power. I have x to the 1/2 times x squared, or I'm sorry, x cubed plus 2x plus 4. And just because we're doing things in slowly here, I'm just going to rewrite this twice. So I'm not actually doing the derivative, so I'm going to do the derivative of that piece first. Order does not matter as long as I have the derivative of one times the other plus, and then on the other side I'm going to do the derivative of the x cubed term instead. Right. So these just mean I have to do the derivative yet. That's what the little tick marks mean. So f prime of x is equal to, okay, so I'm doing the derivative of x to the 1/2. My power rule says I pull down the half, x to the half minus 1, which is negative 1/2. Then this is here, Nothing happened to it. It's exactly the same as it used to be. And then over here I have an x to the 1/2. I'm not doing anything to it. I just need to take the derivative of this. The derivative of x cubed is 3x squared, and then this is plus 2. Now with these, okay, we're just doing the derivative for the derivative's sake, then there's no need to simplify anything. Just leave it as it is. Okay. When we start getting into solving, sometimes we set the derivative equal to 0 and we try to find zeros, and in that case it's important for us to simplify, but it's really not important for us to simplify right now. So right now we're just getting used to our product rule. All right, so I have another one. Again, and these really, and this one as well, I could do this without the product rule. All I would need to do is multiply this. I can actually distribute this, right? It would have, I'd have x to the 3 plus 1/2, so I'd have 7/2, x to the 7/2 plus, and so forth and so on. And if I simplify it, it'll look a lot different than this, but if I simplify them both, then they should match, okay? All right, so let's do f prime of x here. All right, so I'll just write this out again twice. X squared plus 4x times 3x cubed plus 4x plus 1. So I'll do the derivative of this one first and then the derivative of this part second. Okay, so my f prime of x will be, so the derivative of x squared plus 4x is 2x plus 4. I put parentheses because I'm multiplying. This does not change. It still stays here. I didn't do anything to it. Then here, the x squared plus 4x doesn't change. This time I do the derivative of this last term, which is 9x squared plus 4. And there's my f prime. Again, there's no need to simplify, at least for right now, so we'll just leave it as it is. Now the product rule is actually extendable. So on all of the examples that I did, I just had f times g, but in fact I can actually do f times g times h, and it's extendable to as many terms as I want. It's just for each term I have, I'm going to have an extra term in my derivative. So if you notice, and again it doesn't matter, basically each function has a term with the derivative, and then the other two just sit there. So this first term is, I'm just doing them in order from left to right. F prime times g h, right? G and h are unchanged, just the derivative of f. Then I have f and h being constant, g being the derivative piece, and then for the last term I have f and g being constant, h being the derivative. So I can extend it. So again, I could do all of these things without actually using the product rule. I could just multiply these all out and use the power rule. But let's just use it once just for, okay. So I'm just going to write them out. So I'm going to call this f, this g, and this h, and we'll do it in this order. So f prime is the derivative of 2x, so that's just 2. And then g and h stay unchanged, so I'm just going to write them. All right, then I have plus. So this time f stays the same. And then this time g prime is here, so the g prime would actually be 2x. I'm just using my multiplication symbols here, and then h just gets written in here. And plus, I'm running out of space here, then I have f and g unchanged, so that's the 2x and the x squared plus 4. And now this time I need the derivative of h, so that would be 3x squared minus 16x. Okay? And that's my derivative. So I can, in fact, extend it to as many terms as I want to. That's as far as I'm going to go as far as examples go, but you feel free to play with that if you would like. All right, so one more thing that I want to talk about is my students always get confused as to when to use the product rule versus the constant multiplier rule. One of these is the constant multiplier rule, and one of them is the product rule. Right, so the difference is here, my y is the square root of 2 times g of x. Square root of 2 is a constant, and so my y prime will just be the square root of 2 times g prime of x, if you remember going back. On this side here, I don't have the square root of 2, I have the square root of a variable. So it's only when I have a variable in both of my functions or my terms that I actually need the product rule for it. Okay, so my y prime in this case would be, so if I take the derivative of the square root of x first, I'm going to rewrite this up here as x to the 1/2. I'd have 1/2 x to the negative 1/2, so I did the derivative of that, then times g, then plus the square root of x, and then times g prime of x. So that's the literal application. So I only need the product rule when I'm multiplying two different functions together, right? Not square root of 2 isn't a function, it's a constant. So I always have students who will try to use the power or the product rule on this, which actually it will work if you apply it correctly. So let me just write this out here for a second. I'm going to write it out the long way. So times g, and then plus the square root of 2 times g. So this one I'll take the derivative of that, and this one I'll take the derivative of this. So I'm just applying my power rule. So if I do it correctly, the square root of 2 is a constant, so the derivative is 0. So 0 takes g with it. So this whole term here is 0. And then on this side, I do the square root of 2 and then times g prime. I don't know what g is, so I just write g prime like the derivative of it. And so I get the same thing here, right, as I got here. But what I find oftentimes is students forget that this is a constant and it's 0. So be on the lookout, right? When it's just a number, it's just the number is a constant, it just sits there and you take the derivative of the other piece. Unlike this over here where I have a function times a function.